All right, so we're going to use this equation, and then we subtract 1 over 9 initial square. So I have 1. Initially, it was a 6. I would square that, so this becomes a 36. All right, so that's the equation we went through yesterday. If you recall, it was around right there. Well, I told you either memorize them or you need to put them where? In your calculator. What? Yes, but it can certainly relate. This is a very different way to find it, but yeah. All right, so we have that. We do some math and we figure out, I don't know, I never did this. What does this calculate to be? Anyone agree with that? Sorry. I'm sure he said that, I just didn't hear it. 1.816 times 10 to the negative 19. Who has that value? Raise your hands. All right, let the record show that that's everybody. Caleb? Okay. All right, now, what's the energy of the photon release? Good, we have that one, check mark. What's the frequency of light that it emitted? So this is like a physics class now. It's just a bunch of equations. You got to figure out what to put where. So we now need to know an equation that relates frequency, which we had this little v, and energy. And the equation for that one says that E is equal to H times, oops, that was a little bit of wiggle, is equal to that, right? Which we can use algebra to say now that our V is equal to H over E. Is that right? No, E over H, sorry. You okay with that? Okay, so this is an equation that you should know. That was a bad squaring job, but oh well. All right. It's a thingamajig. All right, so now I can figure out the frequency because I have E. It was my answer right here. 1.816 times 10 to the negative 19. And I'm going to divide that by Planck's constant, which is 6.63 times 10 to the negative 34th. And I get an energy, or frequency. What's the frequency equal to? Louder? 81? Times 10 to the negative something? Negative what? Actually, it should be a positive. If you got a negative 54, you got to parenthesize something. Because if we divide by a larger negative exponent than we had in the numerator, this should be a positive exponent. Should be around the 15th. Anybody? Uh-oh. Times 10 to the what? All right, and this unit would be s to the negative 1. Now, a lot of you, this is your first time all year to get an answer right that Emily got wrong. So just take a moment quietly. You can celebrate inside. Just know she's 99 and you're 1. All right. We all right with how to do that? Just a calculator problem. Did you get it now? Okay. All right. By the way, if you don't parenthesize right, what you'll end up doing is taking 10 to the negative 19 and dividing it by 6.63, and then taking all of that and multiplying it by negative 34. And life gets crazy. Okay, the next part of the question said to solve for what? Wavelength of the light, right? Wavelength can be found in 2 ways. We had C equals lambda frequency, right? Or you have lambda equals no. Yeah, I'm trying to do the algebra. Thank you. Either one of those will work. I find this one easier because there's 3 variables instead of 4. So I'm going to manipulate this so it's c over frequency, right? Just algebra. So I just take the speed of light in nanometers, 3 times 10 to the 17th, and I divide it by my frequency, 2.739 times 10 to the 14th. That might show up eventually. Yep. And what number did you get? What did we get? Right around the same? Okay, bummer. I thought this would be between 4 and 700. I was wrong, but whatever. Okay, where did I lose you? One of the first ones that we wrote was C equals lambda times frequency a long time ago. Oh, right here. So now lambda must equal C over frequency. We solved for frequency the previous step. C's the constant. We were off to the races. So C is the speed of light in nanometers usually. All right. So this actually makes the last part of the question unanswerable. I apologize. 1 second, Caleb. The next part says, what color? In my heart, I really wanted this to be between 4 and 700, but apparently I failed. So this wouldn't be a color. We would call this type something else. Do you know what it would be? No, not ultraviolet, the other end. Infrared. Mark Hebert owned that. He gets an A. All right, Caleb, yes. Because there's more than one way to cook this goose. That's how. If you got the right answer, don't argue. Well, what wrong equation did you use? It probably was the right one. Right, that's fine. That was this. When I said there were 2 options, this was the second option. But these are the same. Sometimes when I say or, I write of out of habit. I don't know why. This should be an or, not an of. So you can use either of those 2. Okay, now, when a lot of you saw that big number, you thought that it was ultraviolet, meaning above violet. But remember, a big number in wavelength means low energy, so it would be under red, which we call infrared. Okay, you didn't need to know that, but that's what it was. All right, last thing, it did say, I threw this on for fun, because, I mean, life is fun when we do math. What would be the energy if a mole of these were emitted? So you got to find your energy answer, which was, did we ever solve for energy? Oh yeah, it was the first one, right? You take this one and you multiply it by what? Good. And that equaled what? 09? My fault. Yeah, you have 09. There you go. 1.09 times 10 to the 5th. Yes, sir. Sure. For the whole year or this chapter? Okay. You need to know the speed of light in nanometers. And that's 3 times 10 to the 17th nanometers per second. You need to know Planck's constant, which is h. Sometimes it has a little line right there, but later you'll learn h bar and it's different, but whatever. And that is 6.63. Is that what we said it was? Times 10 to the negative 34. Yeah, that's an h. I don't remember the units. It's just whatever makes it work. probably, joules per second. I think that makes it work. Then we had, if you want, I would put this in your calculator because you actually use HC together quite a bit. And you can just put both, but it doesn't matter. This was 1.989 times 10 to the something. Does anyone remember that? 16th? Negative? And then there was Rydberg's constant. It doesn't really have a letter. Is it RH? Okay. And that was 2.18, is that right? Times 10 to the negative 19, 18. There you go. There might be more, but I think that's it. I wonder when I drink, since my microphone's right there, if you can hear it like go down my throat. Oh well. Really, I'm just recording these and posting them for no one to ever watch. Successfully, we're able to solve that problem. The entire thing except for the color part. Not even a little. All right. Well, I hope that most of you, except for one, felt successful. I don't know what to do with you. No. All right. Next, it's going to get a little bit weird for a while, but it has been for months anyway, right? So along comes Louis de Broglie. He, whatever that word is, that if light can have material properties, matter should exhibit wave-like properties. He demonstrated that the relationship between mass and wavelength was that. So you yourself are a wavelength. Yeah. Yeah, you're just a wave propagating through space. Wow. Pretty fascinating, right? You're welcome to figure out your wavelength if you feel like it, but we're moving on. That's your velocity. All right, you never have to do this in this class. I've never had to do it in my entire life, but you could do it. Okay, Heisenberg showed that the more precisely the momentum of a particle is known, the less precisely is its position known. All right, in many cases, our uncertainty of the whereabouts of an electron is greater than the size of the atom itself. All right, so we call this the uncertainty principle. It's one of the weirdest and coolest things on the planet. Remember, Bohr said that your nucleus was here and that the electron lived on little rings that go around, kind of like planets going around the sun. Remember that part? And he said, hey, they can go up and they can come down, and when they do, they release light. And we just did some math to prove that. All right? But Heisenberg comes along and says, hey, I don't know if this is right, because we can't say the electron lives there. Because if we know right where it is, then it would have to not be moving, but we know it's moving, so we know we can't know where it is. Does that kind of jive? All right, so Caleb's been waiting for this all year. But here you go. The uncertainty principle is your best way to get out of a speeding ticket. Okay? Now, you will probably be arrested if you try this, but give it your best shot. I'm going to pause this. What Heisenberg says is in order to see an electron, like to say, hey, the electron's right there. So like, here's my eyeball. Just go with me here. All right, and it's attached to my head. Just shut up. But I'm looking, right? Just stick with me. In order for me to see an electron, a photon would have to come, a photon of light, would have to bounce off and come to my eye, and then I could say, oh, I see the electron. Like, does everyone see your desk? Okay, that's because photons are coming from the desk to you. You're like, there's my desk. Now, feel your desk. Is it still there, even though you're looking at it? Okay, here's the problem. An electron, if you look at it, by looking at it, it's no longer there. If the photon hits it, what does it do to the electron? It moves it. Right? So, if you see an electron, which we don't, but if you could see an electron, the only thing you really could say is it's not where I just saw it anymore. That's the only thing you know 100%. It's not there. And it's not there because this photon and the electron are around the same size. So when they collide, that moves the electron. So it's not there. We can't really know. We can say, yeah, it's probably there. You okay with that? It's probably there. So we're going to get out of absolutes and we're going to move into probablys. Okay. All right. That just really, it looks like a disaster, but it's actually very well drawn. Yep. I don't think I'm ready to go there yet. Am I there? Oh, I am there. Okay. So let's go here. This caused a problem for Bohr's model. In fact, it was a nuclear bomb to Bohr's model. But the problem is Bohr's model is still correct mathematically. So when ideas in math don't agree, there's some issues. But they can work them out here in a second. Okay? So what destroyed Bohr's model? The uncertainty principle did. You okay with that? We can no longer say it lives on a ring. We can say we think we know where it might be. Okay, so a new model will be made. And you already saw the pictures of it. But the new model is called the wave mechanical model, which we'll go into pretty in-depth detail in a minute. It still has a nucleus. That hasn't changed since Ernest Rutherford discovered it in the gold foil experiment. But now we say that the electron doesn't live on a ring. Oh, that was terrible. We're not going to say it lives on a ring anymore. We're going to say it probably lives in a three-dimensional sphere. Probably. Does it have to be there? No. It will be here most of the time, doing whatever it feels like. Uh-oh. But once in a while, it could be over there. And what an example of that would be, where are you almost always first hour? Here in this room. Are you always here in this room first hour, though? There's a chance we could be in an assembly right now, right? There's a chance you could get called to the office. There's a chance that you didn't feel like going today, right? But most likely, if your parents had to find you first hour, they would start in this room and work their way out because the highest probability to find you is right here. All right, now, we can actually put another electron in here. All right, and then this one's full. So instead of having a second rung now, we have a slightly bigger sphere. And the 4 electrons live in those 2 somewhere, probably. Did I hear the bee what, Cheer? They're weak. Who's in Bert's class later today? Better bring your A game. You got some screaming to do. All right. Then the model gets a little weird, and it's all from math, but it says, hey, now they don't live in spheres, they live in these little thingamajigs. All right? And they're in here somewhere. It's okay if this doesn't make sense. It's not supposed to. All right, and then we get a third, and then we get another one of these dealios.
What if it does make sense? Is that a bad thing?
No, if it does make sense, then you're a mega genius. All right, now, after that, you get another big circle, but after that, you get like Oh, that's supposed to be red. That's supposed to be red. Then you get these, and there's 5 of those. Why is it not red anymore? I'm so confused.
Should we do this model as well?
And then, no, this is good. Then you get bigger ones of these. Yep.
No, you could have just put just like a big black circle there and done the same exact job.
And then you get 5 more of these. Shh.
So beautiful.
And then you get these.
Yeah.
And there's 7 orientations in space. I don't even know how to draw this 7 times.
Yeah, that looks about right. Welcome to our.
All right. Now, what this is these are called probability clouds, and it's describing the probable location of finding an electron now. It's most likely that they're going to be in the center. And the likelihood of finding them decreases as you move out. Heck no. Although one time we had some pretty roses in my garden and I cut them out and I put them in a vase and gave them to my wife and she thought it was so cute. All right. So now, this is our wonderful, beautiful model of the atom. You okay with that? Now, before we move on, I'm going to chop it into its parts. It's made out of what we call S clouds, P clouds, D clouds, and F clouds. All right? And the F, that was for Kylie's sake. All right. Okay, S clouds. They're shaped like spheres. And we'll get into this. Like, you can take notes now, but you don't have to. We're going to get into this farther. And every single cloud that I draw can hold 2 electrons in it. All right? The size of the S cloud depends on the number I put in front of it. So if it's a 1s cloud, it's the smallest sphere that we have. If it's a 2, it's bigger than the first, smaller than the third. You with me? The number in front will tell you the size. All right, then we have what we call P clouds. And P clouds we draw on top of each other, but they're actually 3 independent clouds. One goes that way, one goes this way, and one, I can't do it, but it goes in and out of the board. You with me? But when you're drawn together, oh, that's a bummer, whatever. And then pretend that one's coming out. You with me? Sometimes if I do something, I don't even know what I'm doing. Group. There we go. Hold on, wait for it. I'm smarter than this, I promise. Okay, but together they look like that. Now, how many did I say each one of these can hold? 2. So this one will hold 2, this one will hold 2, this one will hold 2, or for a total of 6 electrons. You kind of okay with that? Just stick with me. All right? So an S, it's a circle. It can hold 2 total electrons. A P, they're like propeller shapes, and they can hold 2 each, but there's 3, so they hold 6. Then we get to what we call D. And these look like you have like you cooked muffins in a pan and they overflowed. Or a 4-leaf flower. Or a 4-leaf clover in your Lucky Charms. All right. Now, the thing about these is there's 5 of them. Where's the infinite? There it is. But they all overlap each other in a weird way. Let's see here. This is fun for me. I don't even care if it's fun for you or not. I don't even know.
2 acres.
Whatever. It's a mess. But you with me?
Yeah,
All right. Now, each one of those can hold 2. But how many were there? 5. So the D clouds can hold a maximum of 10 electrons. All right? Then there's actually still some debate on F clouds, what they actually look like. But the general agreement is that they look like kind of a donut hole, or a donut, sorry, and then 2 things coming out. And there's 7 of those. Each one of these can hold 2 electrons, but there's 7 of them, so they can hold a maximum of 14 electrons. Yes, sir.
I probably don't want to know this, but how do we even get these models?
That you don't want to know that, but I will answer it. These models are 3-dimensional spaces on a 3-dimensional plane that the Schrodinger equation, if you have a number from those regions, will solve the equation. They're answers to a 3-variable equation on a 3-dimensional plane. There's no such thing as a 3-dimensional plane. 3-dimensional graph is what I'm trying to say. So they're just numbers that make these crazy things. Now, the reason there's still debate in F is they're still not 100% sure, like the math shows this, but their observations don't 100% support it yet. All right, now, please remember these numbers. These numbers will be 2, 6, 10, and 14. They will become important maybe by the end of the hour, maybe tomorrow. 2, 6, 10, 14. So let's make what doesn't make sense make less sense. All right. So along comes a guy named Erwin Schrödinger. He developed a mathematical treatment into which both the wave and particle nature of matter could be incorporated. It is known as quantum mechanics. We're supposed to have a guy from ATK come this week, but he hasn't replied still. He replied last week he couldn't come last week, and that he could come this week, but he hasn't said when. He will blow your mind.
Yes. Blow it.
Oh, it's the coolest lecture of the year. It's the only one that's even worth sticking around for because it's not me. All right. Yeah, please. All right. You will notice this is a 3-dimensional graph, right? And the probability distribution of electrons for here, we would probably say would reside in that sphere. Kind of with me? Now, are there other blue dots? Sure, but the overwhelming majority of them would fit inside this sphere, right? So we're saying Schrödinger in quantum mechanics is going to say, we don't know exactly where the electron is, but we have a really good idea of where it probably is most of the time. That's all. Now, to get this probability, it's really just the math answers to what is called the wave equation, or wave function. Now, solving the wave equation gives a set of wave functions, or orbitals, and their corresponding energies. These orbitals they're a numerical value of 0, 1, 2, 3, but we assign a letter, S, P, D, and F, to these orbitals. The bell's going to ring before this will make sense. So wait until the middle of tomorrow for the ending of this story. So each orbital describes a spatial distribution of electron density. Is the bell ring in 2 minutes? It's still like 7 minutes, right? So don't pack up. I'm just warning you that we might leave you like scrambled and not cooked yet. I got you here. All right. An orbital is described by a set of 3 quantum numbers. And quantum numbers, like if you get all this, it's one of the coolest things to me of all of chemistry. If you don't get it, It is just a disaster. You're like, what is he talking about? Class changes, please. But the good news is the test questions from this are not that bad. All right. So what the quantum numbers are as follows. We have what we call the principal quantum number, which is represented with the letter n. The principal quantum number n describes the energy level on which the orbital resides. Now, there are some rules to these letters and what they can be. So the values of n are integers greater than 0. An integer means a whole number, right? So the principal quantum number can be 1, 2, 3, 4 to infinity, but it has to be a whole number. In this class, we will not go past n equals 7. So it will be between 1 and 7. All right. We'll just go here now. All right. So this principal quantum number, this might sound tricky. Oh, hey, just saw my name in circle too. Oh, never mind. I should change my name to that. That'd be fun. All right, anyway. The principal quantum number is the same as the period or row number on the periodic table. Everything we're going to talk about right now, it's about the orbitals and the atom, but it's also about the periodic table. So what these numbers are doing, they're describing electrons that are in the outermost level of atoms. Do you know what you call electrons that are in the outermost level? Valence electrons. So this is a language where we keep track of what's happening to the valence electrons. So if we're talking about hydrogen's valence electron, it lives in the first energy level. And I know that because hydrogen's on what row of the periodic table? It's row number 1, right? If I was talking about calcium, Ca, if I was talking about its valence electrons, what would they be in? We're talking the 4th row now, right? Or the 4th principal energy level. You with me? So when we're going to talk about these numbers, the first one is simply talking about what row the atom lives in. Good enough? All right. I'm going to go on even though you said no. Next up. Uh-oh. Never mind. I thought I muted it and forgot to unmute it. Let's go here. I don't want that. I want this one. Okay, the next letter or quantum number is what we call L. This quantum number defines the shape of the orbital or electron distribution cloud. These have allowed values of, the allowed values of L are integers ranging from 0 to n minus 1. We use letters designations to communicate the different values of L and therefore the shapes and types of orbitals. That's the same slide. Okay, before I get here, I want to do this. I want you to write this little table, S, P, D, F. And then I want you to put 0, 1, 2, 3. So when we talk about this quantum number, which we convert to a letter, which is L, the corresponding language we need to know is that a 0 represents an S, a 1 represents a P, a 2 is a D, and a 3 is an F. So if I was talking about something that was 1 and an S, I would be talking about something in the first row, and its electrons live in what shape? A sphere, right? That's what this language, and I know that you're probably nowhere near to getting it yet, but 20 minutes in tomorrow, I think it'll make perfect sense. Do remember, I'm testing you most likely on Friday. I told you that yesterday.
I didn't know I was